going to talk about MPI-IO. One, because it's a very useful library, but two, the concepts and the optimizations that go on inside the typical MPI-IO library serve as the foundation for all these other IO libraries that we'll talk to and have access to on these systems. And so if for whatever reason your application is not well suited to an MPI-IO kind of solution, I hope that whatever solution you are using is still going to behave in the best ways that MPI-IO behaves. So again, I'm really glad that Shane was able to talk about Darshan in some detail before we got in. I'm going to be using Darshan as a way of showing off some of the behaviors of these IO libraries. Right? As we get higher and higher up the software stack, what's going on under the hood is going to be less and less visible. And so having a tool like Darshan will help us make sure that we know exactly what's going on. Right? I can't tell you how many times I've had an application scientist come to me saying, I'm having an IO problem because I'm doing X. And I say, well, you know, it sure sounds like you're doing Y. Like, no, I promise you I'm doing X. But Darshan comes back and says, no, you're doing Y. Let's try to fix that so that you actually get the performance you expect. It's not a dig on any application scientist. These stacks are complicated and we need all the tools we can to get our heads around what's going on and to confirm what we think is going on, because with the amount of tuning and options that are available, you know, what we expect to have happen and what actually happens could be different. So
hi, Rob.
I have oh, hi.
Just a quick question from the Slack, from where you're speaking to on the previous slide, I think. I just want to know what's an example of a solution where MPI-IO would not be appropriate?
Wow, the short answer is in our world, the HPC world, not too many. We often have cases where applications are using MPI, where they are using an MPI programming model, and so MPI-IO is a natural fit. If you have applications that aren't using MPI but are still doing parallel programming through a task-oriented programming model, or maybe just a very large shared memory model like global arrays, MPI-IO might not be as well suited because you know, the data structures and concepts that MPI-IO are using, and I'll talk about these in a few slides, may not be a great fit for what you as an application scientist are thinking of. And I'll touch on a couple pitfalls where, you know, the big optimizations of MPI-IO may not be, may have some costs, right? It's not all, everything has a cost of HPC, and the trick is knowing where the balance is between the cost and the benefit of that optimization.
Yeah, thanks, Rob.
So yeah, good. Any other questions? All right, let's proceed. One more time for anybody who missed it the first time, we have a GitHub repository with a bunch of different examples, and as we think of more content, we'll be updating it periodically. If we were in the same room and I could walk around the auditorium and to walk through these examples with people, we would have more time to do these hands-on examples. Unfortunately, in this virtual environment, that's not too feasible, but we have simple examples that I hope you will work on, either while I'm talking or during the break or tonight before you go to bed, whatever. And while I'm giving this presentation, I won't have a whole lot of time for us to work on these presentations. It'll be more like the cooking show, right? We put this in the oven for half an hour and out comes a beautiful cake. We'll do the same thing. Here's a problem for you to solve. Think about it for 5 seconds. Here's the beautiful or not so beautiful answer. There are a host of data structures in scientific computing, but for the sake of this example, I'll talk about array-oriented I/O. even the more sophisticated examples will often boil down to some kind of arrays. And furthermore, it's easy to reason about. It's easy to draw on a PowerPoint slide. But the same problems, the way we think about these data structures, even if it's a simple data structure like an array, will apply to any data structure. And there's many cases where that's exactly the kind of data structure you're going to want. As I say, the big concept here isn't so much the array, it's how are we going to decompose that array across the processes, right? We have thousands of compute elements that are going to work on this, this model. And so we have, for example, an Earth model, an Earth system model, and the scientist has decomposed or partitioned the world up into many different patches. Each one of these patches is going to go to a compute element. Now, in the cartoon here, those are very regular slices of a sphere. The application would probably do something a little more sophisticated to balance those patches across all the processes. For one simple example, if you're doing a model of sea ice, right, there are lots of areas in the globe that don't have any sea ice, and you don't need to have a whole lot of computational resources to model that part. So, you know, you're going to do a distribution where most of the work is going to be a small bit of the poles, and that'll be passed out to the application. The important part of that story is there are going to be some application demands on how you share the data. Likewise, there are some storage ramifications for how we store the data. It may be natural to just dump each process's memory out to a file or a log or a store of some kind. That would probably be really fast for that writing phase of your application. But what you've done is produced a kind of a jumble of data that will be harder for other consumers of data to look at. And you know, maybe your application will write many, many times, like a checkpoint that we only restore from in the rare case of failure or restarting after a 12-hour run or something like that. And so maybe that's a good trade-off. But I would wager that many times your data is going to be used by somebody else, either the next step in your workflow, a visualization or analysis step is going to want to look at this data. And so maybe we can think about how to store the data in what we call a canonical view, where the data is not a raw hodgepodge of bytes scattered around, but has some sort of structure to it that another colleague or another component of your science can look at. We think a lot about defensive or checkpointing I/O just because that's historically and still now has been a main source of one of the main sources of I/O, not the only one by far, but its constraints and its needs are pretty easy to explain, right? We've got a state on each process. The application has state, which is composed of some substate on each process. And we want to store all that state in a way that is going to be useful either to us or to colleagues later. And so one way we could do this is with this canonical representation, which encodes the data that we were working with and what we're doing with it, but maybe also does not encode how many processes were involved, right? You could easily imagine doing a state dump or an output file from 1,000 processes, but reading it back or analyzing it with a smaller tens or hundreds of processes on your visualization step. So if we are locked into a certain number of processes, then we've made ourselves fewer options, given ourselves fewer options on how we're going to study this data. Let's walk quickly through the kind of things we might want to say, right? If you just write out raw data, you might, as the creator of that data, as the producer of that data, know what it means, and you could pull back however you like, but more likely either because of time that goes by or because you've handed a code off to another colleague in your lab, you're going to want a little bit of annotations or some structure to say what's going on. So you might talk about the the problem size, how big is this matrix. You might talk about the kind of solution that you're trying to solve here. This is the 10th iteration of the. I'm not a numerical methods person, but I know there are, the chiral solvers or whatever it is, right? This is the 10th iteration of that solver, and it's going to be, I'm saving it here. And additionally, there's the thought of storing this state into one or a small number of things. It may be natural to want to write out, say, a file per process. And that might be really fast in many situations. But then when, again, the consumer of that data comes through and tries to read a little bit of data from 10,000, 100,000 files, that is a metadata intensive operation that's going to be quite challenging. Likewise, taking that data set and putting it somewhere else. Well, you have to collect all those files, manage those files, make sure they don't get out of sync. We typically find that a small number of very big containers, objects, files, is much easier to manage than many small files. And then we touched on something called a collective. What does it mean to be collective? In many cases, we have phases of I/O. We compute for a while, and then every process is going to do an operation. As Phil mentioned earlier, the way that these storage systems work, a single process really can't drive the maximum performance out of these storage systems. But if all these processes are working together, we can then hit the advertised bandwidth numbers from these storage systems. But it takes hundreds of processes to do that. A collective operation where the library knows all these processes are working together, the library can then manage and coordinate that access so that we get the best performance. I'll talk more about that in a few slides. Running a little behind schedule, so let me just talk a little bit about these examples. Right? We're going to start with the simple problem here is, how do we write an array out to the storage using MPIO eventually, but in this case, just using a basic C program. I have this time around written Python versions of all these problems, but I'm not a terribly competent Python programmer. You will probably find it to be a very primitive and non-idiomatic Python script. If you have any refinements you'd like to make, send a pull request or a patch. I'll be happy to adapt that. Or if you don't like Python and you have another language you want to try these out on, go right ahead. It's just that your presenters, myself included, are really fluent in C and much less fluent in other languages. We have access to 2 machines, maybe a few more this week, but we're going to, for the I/O part, we'll look at Theta and Ascent. And in the Git repository, there are some environment files that will load up any environment, that will load up all the modules we can imagine you needing, and hopefully that will get you going about how to figure out the exact naming convention of all these modules on the different systems. One note: if you do like Python, I had trouble getting MPI 4Pi set up on Ascent, but Theta's MPI 4Pi was working pretty well. So if you are dead set on trying this out in Python, I would recommend Theta. Otherwise, Theta or Ascent will be just fine. Or in this simple case, for the first 2 hands-on examples, you can do it on anything really, because it's just using simple C routines, simple I/O routines. So when we think about writing data, we have the array. It's an allocated chunk of memory, and then there'll be some extra piece of information describing that chunk of memory. And I would imagine it would look something like a 3-element struct describing the dimensions of the array and which iteration of the simulation we're on, or something else. You can imagine putting a few things in this metadata, but for the simple example, I think these will suffice. Another point I want to bring out is, you've probably seen this in the MPI section of this week. If you are sending among processes an MPI description of the data, it will be much easier if that is a single memory allocation that we then treat as a 2-dimensional array versus what might be your first guess, allocate all the X's and allocate the Y's and try to maintain all those pointers. Definitely possible using MPI data types, but not quite as straightforward as just using a single memory region. Yeah. We've already touched a little bit on the different APIs available to us. So I'll start with our least favorite, but always available interface, the POSIX IO interface. This is at this point, 60-year-old interface created, not 50 years old, created when IO was one CPU writing to one slow storage device. And it has not really changed much since then, even though our CPU scales have gotten larger, not just on single nodes, but across many nodes. And our storage has gotten more complicated. Our networks have gotten more complicated. It has, if you look at this interface, it's a simple example of what POSIX IO looks like. You won't see much parallel, you won't see any parallel concepts. When a process opens the file, all you tell the library is that I want to turn this file name into a file descriptor. And that file descriptor only has meaning on the one process. You can't share that with anybody. So everyone has to open the file. When we write data, we don't have much information about the kind of data we're writing or where we're writing to. All we know is that here's a chunk of memory and it's going to go to this location in the file in this linear fashion. Similar, when we read it back, when we close the file. There are a few routines that are a little more sophisticated in POSIX, but not by much, and certainly not compared to what's available at MPI or higher level libraries. I can't really speak too authoritatively to Fortran, but I do know that as you write out these records into a file, certain compilers may or may not pad the records, and so you have an interoperability problem here as well, making sure that when you read back this Fortran generated data set, that the compiler either skips over the padding or is aware there is no padding, whatever the case may be. So even though the POSIX API is in many cases underneath the hood in MPI-O, the users, the libraries or people like you, will hopefully not program into it directly, will have a more richer interface with which to work on with it. So now we're actually going to write some data out to our disk. This is going to be super simple. We're just going to take a routine called write data, give it a file name, and it will do something for us. Now, in this simple example, it will be POSIX, but in other examples, that write data routine will be more sophisticated. Running that code, I think you've probably run a few examples over the week so far, but we've got a queue which is dedicated for us this week today on Theta at the ATPESC 2021 queue. Ascent, you can run wherever you like, willy-nilly. It's a test cluster for situations just like this. I've got a job script. If you would like to write, if you want to submit the job on your own, go right ahead. But the submit scripts for Ascent and for Theta will wrap up some of those details. You have to worry about it. For example, on Theta, jobs are run with AP run. On Ascent, it's dsub. And they're also going to point you to the right file system. If you do the IO to the NFS directory on Theta, it'll work. You won't get, it's not great, and it's not being very friendly to the other users of the NFS file system. On Ascent, I don't think it's even possible to write to the home directory. The jobs are only able to write to this global file system, this parallel file system. All right. So what happens here? Right? POSIX is, again, very simple. So you have to issue two system calls, two write system calls, one for the header of the data, one for the actual data. In this example, we have a buffer create function, which just seeds in sequential numbers into an array, sequential integers into an array. And then we write it out. Now this is a binary data. So if you try to open this file in your text editor, you'll see some garbage characters. Either you have a custom reader that would understand this binary format. You can also use a tool like OD, it stands for octal dump, but OD-TD will give you decimals. And you can see in this file, there's one iteration of a 5x1 array, and its contents after that, the fourth 0, 1, 2, 3, 4, and so on. So here you go. Now you can prove to yourself that you actually wrote data to this file and it wasn't just random data. All right, but that's serial I/O, and we're in a HPC environment. We need to do more, do some parallel computation, but maybe we don't want to do parallel I/O. We'll just send all the data back to rank 0. That's fine. It has a couple problems, right? There's a bottleneck. All the processes are going to have to talk to one process that can't do anything else until everyone gets back to it. You have to have enough memory at that master process to hold all the state from all the other processes. And then again, the recurring theme here, when you do I/O to these parallel file systems, one process, one node isn't able to get the performance that 10 or 100 or 1,000 processes can do. However, we're building our way up. So now it looks a lot like POSIX, except we've added this gather step. And I'm not going to spend too much time talking about MPI intrinsics, but we use gather. It's a collective routine. All the processes participate, and it will be more efficient and better performing than having every process do a non-blocking send to rank 0, have rank 0 schedule all that and refer to it. But now rank 0 finally has all the data, n procs worth of data, and we'll write that out in very similar to the first example that we saw. All right, so there's a couple problems here, right? We're just writing raw binary data. What if we had different endianness or different architectures? That is going to, every so often, a new machine shows up with an esoteric platform. In the old days, back in the 90s, there were lots of different platforms and lots of different choices, and platform portability was a big concern. Today, it's not as important, but down the road, there probably will be a new machine, a new architecture. And so we are implicitly writing this data in the way that the Theta or the Ascent machine natively stores the data. What would be even better is if we had a format, a file format, and we'll see this in the other libraries, that gave you a explicit, defined file format, and then that would be portable across any machine. This is a really simple example. Every process is writing out a column of data, and so we didn't need to use a very sophisticated data description. But if we were going to write out every process is writing out a row of data. If we were going to write out a column of data, we would have to do something a little more sophisticated. And then again, the header has impacts on how data is laid out, and I am way behind schedule. So let me start moving through things a little faster. I would encourage you to think about what kind of I/O you see from this, and then go find your log file from this example and look at Darshan data for it. And that's going to be pretty great, because you'll try all the things that Shane had mentioned in his talk. All right, let's get into parallel I/O quickly. MPI is a message passing interface, and it may seem at first odd that a message passing interface has anything to say about I/O, but it's not that different if you think about it. Take a step back and think about what are we doing when we send a message to a recipient. MPI has data types, so we are describing the data structure in memory of what we want to transmit. MPI provides a standard way of doing that data exchange, ignoring the network and interconnect that's connecting these sources and sinks of data. And there's this notion of collectives and non-blocking, these concepts that are really helpful for scalability. Well, if your recipient isn't another process that's going to send or receive data, but it's instead a file system, all those concepts still apply. We can describe the kind of data we want to write with MPI data types. We can use collective I/O to coordinate the way lots of processes write that data. And we can use the fact that MPI is always available to ignore each file system that we're writing to and trust that the MPI library will have implemented the right thing for the right file system. Now, there was a talk in chat about having set-aside processes or dedicated I/O processes. And one thing that many MPI-IO libraries do is this idea of data transformations in the collective step. We have every process doing a little bit of IO, and then a smaller number of processes called IO aggregators will then collect all that data and then do the IO on behalf of everybody else. Now, this is a blocking step. All the processes are working together at the same time. So we're not doing any latency hiding or anything like that, but we are doing the kind of data transformations that can make or break performance to these file systems. So what does MPI-IO look like? If you've done any MPI programming, some of these concepts will look really familiar. When we open the file, we have a communicator. The communicator just says, here are all the processes that are involved in this file. We have a file view, which is a way of telling the file system, hey, we're about to do some IO to these regions of the file. And each process sets a file view accordingly. And if you're doing writes, you can set to non-overlapping regions and then write that data out collectively. In this case, we've got the typical buffer count and data type tuple that you see in many MPI routines that describes the memory region, how much of that data to write, and what the data type looks like. What is the structure of that data? And in this case, we've described a data type that has every process writing to a different region of the file. And even though there's this very sort of scattered approach, these processes under the hood will undergo some transformations, and this could be a very efficient IO operation, even though it looks kind of like lots of little small pieces. So a couple things to point out when you're looking at MPI-IO call. The collective nature of MPI-IO is explicit. So there's an underscore all. There are independent versions of the routines as well. I won't talk about those too much because there's not much the library can do to optimize those. And then every process, because this is collective, every process must participate in the collective. Even if you have no data to contribute, that's fine. It may be that the process with zero data turns out to be the best connected to the storage system and will be the one that actually does all the IO, for example. And so two things to keep in mind. This requirement that all processes participate at roughly the same time can be a bottleneck, can be a hindrance too, right? If you have one process that's busy doing compute, none of the processes can do collective IO until everyone catches up. Something to bear in mind when you look at your IO performance. So let's do some real parallel IO here. We have again, multidimensional array, and we want to have every process write to this array, write a row out to the array. Okay. So there is a small header. So rank 0 is going to do a little bit of independent IO here. You can see it because MPI file write has no underscore. You can also see that I've checked the return code for every operation in MPI. It's very easy to ignore that and then, trust me from experience, puzzle for way longer than you should why IO is not behaving the way you expect it to. IO errors are not critical errors typically. The library will trust that you will check for errors and then handle them, either retry them or do something else. So you won't get an assertion or an explosion if you fail to open the file and then try to write to a null file handle. You'll just get silent errors unless you check for them. That's one of the drawbacks and benefits of being a C programmer. So there's independent IO, collective IO. It's going to look a lot like, in this case, it's going to look very similar to the POSIX case because all we're doing here, there's no sophisticated data type here. We're skipping over a few bytes with the underscore at suffix there and writing at a specific location in the file. Now, when you run this example, I hope that you will think about what you expect to have happen and then generate a Darshan report and see if that is what happens. There are a couple of things that might surprise you, right? You might find that your 64 processes made 64 MPI-IO calls, but then that was only 2 or a small number of POSIX calls, or not, depending on whatever optimizations the MPI-IO library implemented. And hopefully you'll see a transformation between the number and size of the recalls. Darshan can tell you, hey, your MPI-IO call made 64 4-byte writes, and that turned into 2 4,000-byte writes, something like that. And again, typically the rule of thumb for these systems is smaller IO operations give you better performance. So a smaller number of larger IO operations will give you better performance. And hopefully you'll see the IO library doing all that for you, so you don't have to do it in your own code. No, so speaking of things that the MPI-IO library will do for you, it's worth discussing just briefly this concurrent access to a shared file system. This is going to look a lot like shared memory, but the problems are even bigger because we're dealing with a larger parallel state. In order to enforce the data consistency across processes, the file systems typically will have regions of the file, we'll call them blocks, and those regions will be guarded by a implicit or operating system level lock. And if you have 2 processes writing to the same region of a file, each process will acquire these locks, do its write, and then release those locks. And if they are writing to separate regions of the file, that can happen concurrently. But if they're writing to the same block or page of the file, there's going to be a serialization point. And so hopefully the MPI-IO library will sort things out and make sure that that doesn't happen. Again, I only want to talk about this so you know it's happening behind the scenes. I hope you don't have to worry about this in your own code. Hopefully you can lean on the MPI-IO library. So here are a couple of different examples, right? It's very easy to imagine, say, Lustre with its 4K page boundaries. 4K is not 4 kilobytes isn't a terrible number. It may be the case that you already have a natural data distribution where everyone is going to write their own 4K chunk of data already. But all you have to do is put a small header in the front of the file, and all those naturally aligned 4 kilobyte reads and writes are shifted just a little bit, and now they're touching multiple block boundaries, requiring a whole lot of serialization. And if there is a different distribution going on, not row-oriented, but maybe column or blocks, the story is even more complicated. Again, but you can rely on the MPI-IO library to sort of resolve that. Typically, that's done with something called these IO transformations. Right? Every process has described what they're going to do and where they're going to write it, and the library can reorder things and shuffle things around to make that IO operation perform better. Let me see here if I got a good example of this. Yeah, so one transformation is data sieving. This is the one transformation that independent IO can also do. And data sieving shows up in many different contexts in the software stack, not just in MPI-IO. Data sieving in the RAID context is a read, modify, write, because those are the 3 steps we do. We read in a region. Sorry, why would you do this? If you're going to make updates to a region, but not update the entire region, you may decide that, so your 2 options would be many small operations to update the specific changes you want to make, or we could rewrite that entire block in one go. And this is one of those areas where it helps to have a mental model of your storage performance, because of course you can imagine maybe you have a 16 megabyte block and you're only updating 2 or 3 bytes of that. It might make more sense to just update those individual regions than it would be to write the whole block. But in many cases, that's not the case, because as Phil mentioned, the latency for these operations is so high that once you've done one IO operation, If you have to do more than one or two, you're going to be in trouble. So if you're going to do these non-contiguous updates, right, we're going to read in the whole region to memory, make those updates in step 2. That's the modify step. And then write out the whole region. And it might seem weird that you're going to read in way more data than you need and write more data than you need. But again, that has to do with the nature of these storage systems. Doing fewer operations has such a benefit that writing out extra data is not that high a cost to pay. Another thing we can do, another transformation we can do is a transformation that is more aware of these different lock boundaries on the system. And we call this two-phase collective buffering, where each process exchanges the kind of data they want to do and where with each other. And then a smaller number of IO aggregation processes carry out that operation in a way that's most natural to the file system. On GPFS, that would be a very large block. On Lustre, that would be something a little more sophisticated, doing some shuffling around to make sure that every IO aggregator writes to a single, what they call OST, a single Lustre server. And these different approaches are complicated enough that I would encourage you not to try to do this yourself, but rely on the MPI library to do it for you. For example, one approach, this block aligned approach, works great on GPFS, but if you do that approach on Lustre, it won't work well at all. You get much worse performance. Similarly, this OST-oriented approach that works well for Lustre does not work great at all for GPFS. Good news is the MPI libraries on these systems know that, and you don't have to worry about it at your application level. Let me talk real fast about an application. This is it's a combustion code called S3D, and it's trying to write out multiple arrays of data to a file. And a while back, I want to demonstrate what happens with these different optimizations. So if we turn off all the MPIO transformations and we write out these 4 arrays using parallel netcdf, but I'll get to that later, using an IO library, route 4 arrays, and we do it without any optimizations at all, it'll take half an hour. And the average bandwidth here, this is a very small amount of data, 6 megabytes. So we're talking about, a ridiculously small amount of, such a poor performing time that you almost think your problem got stuck in a loop. Turns out it was just writing very, very slowly. So these 100,000 IO operations is terrible for this file system. So let's add one of our transformations. The data saving transformation will move more data, now 80 megabytes instead of 6, but we're doing much fewer operations. We are still doing 64 MPI IO calls, but those turn to 80 POSIX reads and writes. We're doing a data saving operation here. So we've cut the runtime down several orders of magnitude. Now the next step, this collective aggregation, collective IO buffering, this collective buffering optimization is kind of the best we can do here. We're down to a half a second of IO. We've done exactly as much IO as we need to do, and these 64 MPI IO writes from however many processes there were devolved into one operation for the netcdf header, and then one operation for each of the 4 variables that this problem was trying to store. So I've talked a lot about writing, but we can also read with MPIO, of course. So let's take that process, our toy example, and we wrote everything out row-wise. Let's have every process try to read one column, and they're all going to read the same column. This is a little more complicated. We have to use a file view, and we have to compute where we're going to read, but it's not too sophisticated. This operation, reading one row or one thing out of an array, would be trivial in netcdf, and we'll see that in parallel netcdf in about 10 minutes. but it's a little harder to do in MPI. Not impossible, but just more bookkeeping, more legwork. So we're going to create an MPI data type. We're going to use the subarray data type. You'd have to describe how many dimensions there are and what's the global size of this array. So logically, the array is, number of processes by y big, and then we have to tell this data type creation routine where in that global subarray we're going to write with the starts and counts elements. So in this case, we're going to we have global sizes. The subarray is going to be one whole column, but only one of those columns. And where's it going to start? It's going to start at the first X value, and it's going to read the whole way down. But it's going to start at the middle of the array. In this figure, one of the just one of the columns in the middle of the cartoon array. All right. So once we have the data type, then we pass that into. We do two steps. We set the file. Once we open the file, we set the file view, telling it to skip over any headers that might be in the file, and then we tell the this effective file type is, when we do we talk about numbers in the file. Are you counting bytes? Are you counting ints? What are you counting here? And then subarray is the type we created, and then we write that out to the file with MPI file. Sorry, when we read that, sorry, we commit. Yeah, we set the file view, and that has told the library what to expect. And then the read operation happens on just that one window. Now, unlike writes, it's perfectly fine for everybody to read the same data, and it'd be interesting. It's interesting to see how different MPI IO implementations handle that. Everybody reading one region. Okay. So again, this is
Rob.
Hey, Phil.
I have a question from Slack. Eric says, I've spent quite a lot of time trying to hand optimize MPI IO hints. Are there any tools that can assist in tuning these hints?
Yeah. So as you can see in this example, is an info object when you open a file or when you set a file view. These info objects, like Eric's asking about, are tuning parameters. We call them hints that the library can use to guide how it's going to do its operations. And setting them can be a real headache because there are quite a few of them, and it can be hard to know what the right answer is for your system. So I can certainly sympathize with Eric trying to try different things out and figure out what the best hint is. Unfortunately, the best solutions we've come up so far with, have been to burn 2 billion CPU hours to do a genetic, a machine learning sort of check and testing, and that got you a set of hints that worked really well for most cases at the cost of 2 billion CPU hours. And I'm not exaggerating. It was a lot of CPU hours. Or what happens mostly is someone like me or my colleagues will tell a user, why don't you try this hint? I have an intuition that it might work well. So yeah, automatically setting hints is kind of the holy grail. We've been thinking about this for quite a few years, but the challenge in knowing what the right hint is and how that would impact your application or applications in general has proven to be a little bit of it's hard to nail it. It's hard to nail down that space in a way that we can say, yeah, just always set this hint, always do that. So strategies for picking hints. Looking at Darshan data can help a lot. If you, for example, if you do a collective IO routine and you're expecting the library to turn these operations into something more sophisticated, but you didn't see any transformation happening, there might be a hint that you could set to force the library to do this transformation. The library may have thought, well, this is a simple IO operation, I won't do any transformations, for one example. Another approach is if you know something about your data, you know that you're always going to read and write in certain amounts of data. You can tune some of the buffers a little bit to be bigger or smaller. I would say that in the time I have, I really can't spend too much time getting into the details of MPI-O tuning. But this is something I'd be happy to talk about more during breaks or even after ATPESC. It's actually a pretty big topic. How to get the right, how to tune these stacks is an ongoing area of research.
All right, thanks, Rob. Real quick, I might want to do a time check. You got about half an hour left for the parallel SCDF stuff. I'm not sure how you wanted to split time between the two.
That's right. I've got to wrap this up pretty fast and move on to parallel CDF. So let me get through this quickly and move on to. Thanks. I really love this story though. Before I move on to NetCDF, we had this case where on a new machine that we got from the vendor, we tried using MPI-O and got very bad performance. And the problem was, just as Eric said, some of these tuning knobs, the defaults were not appropriate for this new machine. It was a second generation of a machine. The hints were set for the previous generation. And so any user that took our advice and tried to do collective I/O would observe a terrible performance and would probably get very frustrated and give up. But if we adjust these defaults just a little bit, it was just one line in the library, we're able to get better performance. And so I tell a story to encourage users to try out these techniques, but not to get discouraged if they aren't immediately productive. There's lots of people who want to see you succeed, and it probably isn't your fault that you're getting bad performance right away. There's probably there are many pitfalls in the I/O stack, and if you are running into them, somebody else probably will too. And so don't suffer in silence. Don't suffer in silence, but bring in an I/O person to help fix this for not just you, but everybody else. All right. Oh, so much I love to talk about, but yeah, if you look at the Darshan data for different benchmarks, it's fun to compare different machines. Go ahead and do this on your own and confirm that these numbers are what you think. Let's move on here. There's lots more to talk about. The Using Advanced MPI book, this green book, has a pretty great section on MPI-O specifics. Again, I don't know if you're going to use MPI-O directly. You probably will be better off with a higher level library. I did want to plug MPI4Pi though, because like I say, even though I'm not a Python person, there's a really great community of people who are helping folks use all of MPI's features as great as possible. Python makes doing tricky things in MPI a lot easier, and as a result, MPI4Pi has been a great way to exercise some of the hairier parts of MPI-O. All right. Let's talk about. I'm glad to see that Phil's been chiming in on Slack here. Are there any outstanding questions or any items we should talk about MPI-O before we move on to the next topics? Fantastic. Let me go on now to the next one here. Yeah. So the next 20 minutes or 25 minutes or so, I'll cover parallel NetCDF, and then my friends on and then Seren and Scott will cover HDF5. And I like to do this order of the high-level I/O libraries because there are many different solutions to how do we tailor the I/O stack for specific applications, right? And so parallel NetCDF was one approach, but so too is HDF5, and they have different trade-offs and different levels of sophistication, and some are better for certain domains than others. I like to talk about parallel NetCDF first because it's a fairly simple data models and a simple library. It's just dealing with arrays. In fact, it's pretty straightforward to implement as well. It's very friendly to MPI-AO because you can't really change things after you've created them. HDF5, by way of contrast, is much more flexible, and that flexibility means that it's a little more complicated to implement under the hood. So we'll start with parallel CDF, talk about its what it can do and how it works, and then Scott and Seren will give you the next turn of the crank in terms of sophistication. Okay. But these libraries, regardless of their differences, do have many things in common. They are providing a portable, self-describing file format, which means once we create this data, no matter what machine we're on or how many machines we're looking at, we can still see what's on here. The data has been annotated, perhaps, with human readable descriptions of what's going on in the file. You can put comments in it's basically putting comments in your code, but you can put comments in your data. And so when I create this multidimensional array using a library like ParallelNet-CDF or HDF5, anybody can look at this data set and see, oh, hey, it's a two-dimensional array. It has these properties. I know how to work. I know how to work with this. I want to also make sure that I emphasize, while I will speak about ParallelNet-CDF, a lot of the work these days comes from our friends at Northwestern. And if you have a bug report about ParallelNet-CDF, you'll probably hear from Wei King about a solution for it. If you've done any climate or weather code, you've probably worked with a NetCDF data set. The Unidata folks at UCAR this data set has been around since 1992. And so there's lots of, this library, this interface has been around since 92. And so there's lots of tools and libraries that are already using this data set. But for many years, it was only serial. So in ParallelNet-CDF, we kept the same file format, but provided a parallel interface. A few years after ParallelNet-CDF showed up, the NetCDF library added parallel I/O features. So there is a little bit of confusion here. We have NetCDF4's parallel features, and then we have ParallelNet-CDF. All I can do is apologize for the confusion there, but I'm going to focus on ParallelNet-CDF here in this talk. If you want to work through the examples here, that's great. We also have we call a quick tutorial, which walks through all the ParallelNet-CDF features, and you can try that out too, either in here or on your copious free time. So the nice thing about these libraries is that, again, we have an I/O stack. If you target ParallelNet-CDF, it doesn't matter whether you're running on Summit and writing through Spectrum MPI, or you're running on a Linux cluster and writing through MPitch-based MPI. You'll still look the same, it'll behave the same. It's going to be the same interface no matter where you go. The way that we think about, well, all these high-level I/O libraries, on the left figure here, the application is thinking about its science. There's a patch of ground with a surface with barometric pressure, or a region of the atmosphere with a temperature, and that is the way that the science is thinking about the data. To store that data, however, we have to turn those concepts into offsets in the file and allocations. So in the middle here, this table shows that the header in NetCDF and ParallelNet-CDF will describe, hey, I've got these variables with these properties and these attributes. So we know the units we're dealing with, we know the size, and then as you can see in this figure, a start offset, which is the one place where we talk about specifically where on the file to find these pieces of data. One complication in NetCDF and ParallelNet-CDF is the way we handle variables that change over time. These record variables have a performance implication. Right? If you only have one record variable, that's not such a big deal. But if you have, in NetCDF, we have a header which describes the variables. These non-record variables, variables that we know are going to be X by Y by Z, are the easiest to work with in parallel NetCDF and NetCDF. They allocate some space, they're in the file, and no problems. But the variables that grow, these record variables, like for example, a temperature sensor out in the prairies collecting temperature every 5 minutes or whatever the frequency is, we'll keep adding one of these records to a record variable. And maybe your data set has 10 of these record variables. If you try to read back the data, they'll be highly non-contiguous because you're going to read the data in this interleaved fashion. And that's a performance pitfall that you may run into in parallel NetCDF. All right. When you use NetCDF, you have this bimodal interface. First, to write data, you have to declare, I'm going to have these many variables of this shape and size. And then once you've finished describing them, then you can write to them. And it's a little bit of a headache, but it isn't so bad. Most people know what they're going to do. And by doing that, the library has a lot easier time of writing out that data efficiently. So if we think about an example here where we're going to write a parallel NetCDF version of our array examples, a lot of details are going to be hidden from us. There won't be this idea of MPI file views or MPI data types. Instead, we're going to operate in a more natural way to our application, operating on elements of an array. But like MPI-IO, there are still collectives with the underscore all. We have collective routines to write variables. And then after we're done, we can check our work with either a parallel tool, or we can use the serial NetCDF's NC-dump tool to see what happens. So let's talk about it here again. If we look at writing out this array, again, every process is going to write out one row of data in this array. So it's logically and there's a figure 4 by 5, but and each process is writing out a 4 by 1 row of the data, but you could have a different decomposition where processes write out multiple rows. That's the important thing here is I want to talk about the 2 steps. First, we have to define the dimensions. Then we associate those dimensions with the variable, and then we can annotate the variables with attributes. And once we've done all that, that's the define mode part of the step 1. Then we can switch by ending define mode into data mode. And once we've computed our start and our count, which in this case is not too complicated because we're just doing elements of arrays, then we can write out the data collectively with an NC-MPI put var int all call. So in this case, right, put, we're writing the variable. Var a, we're doing subarray access. Int, it's going to be integers, and all will be collective. Here we go. Talked a little bit about this already. Let's get this one and data mode. These days, I don't think you're going to find this jump shot tool too many places, but I thought it was really useful to see what's going on under the hood when we run a parallel NetCDF benchmark. And in this case, we ran it across, I think it was 32 processes. And you can see in this timeline view, JumpShot is capturing all the MPI-IO calls for us. We didn't add instrumentation for parallel NetCDF. But in this case, we write out a checkpoint for this IO kernel. The blue bars are collective write calls. The nice thing about MPI, about parallel NetCDF, is that it maps very closely to MPI-IO calls. So if I see a blue bar that represents a collective write of a variable, I can infer pretty easily that that was a NetCDF, a parallel NetCDF call. All right. In the upper left-hand corner, there's the header IO, but then you have these variables being written out. And what's nice about this timeline, we can see that some processes are spending lots of time in collective writes, and some processes are spending no time at all. That is an artifact of this MPI-IO two-phase collective buffering that's going on under the hood. Some processes are IO aggregators. Other processes are simply contributing data to that aggregation. So you may not have jump shot where you're doing your work, but we all have darshan, and we can generate a report and look at it. You can think about how do these parallel netcdf calls correspond to MPI IO calls and correspond to POSIX calls. I'm going to skip this part a little bit. Well, I like this example a lot because here's an example of not really array writing, but particle writing using a simulation called the HACK code. It's a cosmology code. And cosmology codes are trying to simulate the universe. And when we look in the sky and we see structures in the galactic, we see galaxies and nebulas, how do these all form from the Big Bang? And these simulations are literally modeling everything. We start off with initial conditions, a few physics models, and then run for 13 billion years and see how this looks. Well, there are, in this case, there was something like 2 billion particles, trying to capture the state of the universe. And writing that into parallel netcdf is a little bit harder. It turns parallel netcdf from an array-oriented data structure to more of a particle tracking structure. But we do that with arrays. The arrays have in their X dimension different descriptions, but each of these tables is collecting a list of particles. So, with a little bit of work, you can apply parallel netcdf to a variety of contexts. I'll gloss over the implementation details. You can refer to them later if you're looking at applying parallel netcdf to you. All right. So the time I have left, I'm talk about reading. Right? Reading is not too hard. We can compact it all into one kind of small slide. Let me walk through the different steps here. If we are handed a netcdf data set and we want to read it in parallel, we have to figure out, like I said, I've said a few times, these are self-describing file formats. And we have all the tools in the library that we need to interrogate the file and figure out what's inside of it. So first thing we're going to do, we're going to open the file, in this case using every process in the communicator, but you could partition the communicator other ways. Excuse me. We're going to open the file and get back an identifier. Then with that identifier, we can then query the file for how many dimensions are stored in netcdf, how many variables are stored, how many attributes, and are there any record variables. Once we know that, our little C reader can allocate data to pull in more information. So in this case, we're going to figure out, we know there are going to be, say, 10 dimensions in this data set. How big are those dimensions? We can rip through there and get the sizes of those dimensions. Then we can figure out with the variables, which of those dimensions are associated with which variables. The dimensions in the file could be associated with all the variables or none of the variables. And now we know, say there are 6 variables in the file, and each variable is going to have dimensions, and now we know. And when we go on to the reader, we know how we know where to decompose this variable and then do the IO. So these inquiry routines are they work on any data set, and you can know as little as possible about the data set. Often, your colleagues will follow what's called a convention, and you'll be able to skip some of these steps. But if you didn't know anything about the data set, these three calls, you can figure out any data set that you've get your hands on. So if we're going to read our simple array, what does that look like? Well, we're going to open the file. We're going to ask about the variables in the file. We're going to get some identifiers and dimensions from the data set. And then when it comes time to read it, we don't have to worry about data mode or define mode if we're reading, because we're not making any changes to the data set. Furthermore, we don't need to worry about MPI file views or data types. We can just do the operations in terms of array types, or thinking about things in terms of arrays. So in this case, just like with the MPI example, we're going to read a whole column of the array, but everybody's going to read the same middle column of the array. Now, lastly, I'd like to talk about, okay, before I get into extra features of parallel NetCDF, is there anything I can spend a little more time on before I go on to any aspects of reading or writing a parallel NetCDF file I could touch on?
We have a question from Slack from Christopher. He says, is there a NetCDF, parallel NetCDF model for interleaving record creation and writing? For example, write A, write B, write C, that affects the writes in sequence, but does not know in advance how many records will populate the file.
Well, so in parallel, in NetCDF and parallel NetCDF, the assumption is that you pretty much know how many variables you're going to be stashing in the file and the rough idea of their sizes. As if you add new variables to a data set, you write, and then you switch back into define mode, add more variables. That'll mostly be okay. At some point, your header won't be big enough to hold that variable, and we have a pretty big header. We pad the header out pretty largely in parallel NetCDF at least. And so you can add a lot of variables before triggering a rewrite of the data set, but that rewrite is very, very expensive. If you don't know the sizes of the variables and you're doing these record variables, that's not too uncommon in the weather communities, because they are typically reading from sensors, right? And the sensors are periodically going to add another record to these record variables. So you would define the variable with the dimensions you did know, and maybe latitude and longitude and altitude, and then maybe time would typically be your unlimited dimension. Unlimited is NC_unlimited is the way you would define that. And with that unlimited dimension, then you are appending records to these files. Perhaps in the HDF section, you'll see how that might be a little bit easier to do, given HDF's more sophisticated data structure and flexible file format. But there are situations that we see where people are regularly collecting and appending data to these variables, and then you have these record variables to work with. Thanks. So again, on the topic of working with many variables, the recurring theme is always, how can we do more I/O with fewer function calls? And one way we can do that is this another recurring theme of, we're going to describe more data and then execute it all at once. So this, I guess there's a typo here. That should be a operation combining, because it works for both reads and writes. But in this case, we're going to combine two writes. So we have the purple variable and the gold variable, and the caller will use these it's non-blocking, but really what it does is describes the I/O and then executes the I/O later. So the I in here is just like with MPI routines, is an indication that it's non-blocking. I for returns immediately. I put Vera says, okay, I have this data I want to store in a file, and you get back a request thing. Then you do that again for a second variable, and then you can wait collectively for those variables to be written out to the file. And so what will often happen if you do this is you will combine all those operations into a larger I/O request. You won't pay any coordination or synchronization costs until later, and you'll end up with a much more friendly request for the file system. And this can result in some pretty nice performance gains. We haven't talked about the Flash astrophysics code too much, but they've worked with us for a long time, and they run on every machine you can think of. They're modeling supernovas, the detonation of when a star goes from happy star combusting, fusing hydrogen to helium, and then at the end it goes supernova, right? So we want to understand this better, and the simulation is a very large, sophisticated simulation. It runs on every machine you can think of. But they had a problem. They wanted to get better performance, and they had a choice. They were writing out a series, like 30 four-dimensional arrays capturing the different states of this detonation. And the choices can be either to write that data out one variable at a time, or maybe you have a 5D variable where the fifth dimension is like a variable identifier. And then they could write out all 30 variables in one go. However, that changes the file format, which means visualization tools and other people using this data set have to update their stack. It'd be great if they could keep the file format exactly the same. Well, if you use right combining, you can do just that. And here, I apologize if you are reading colorblind, but the bottom line here is pretty poor performance for this operation. And then when we did the right combining and wrote all the variables at once, we were able to get almost a factor of 2 better performance. And that factor of 2 performance came from being able to give more information to the MPI IO library, optimize the request better, and then see this gain. So go ahead and try this out in the examples. Take a look at the Darshan output to see how that looks. And when I tried this myself, the vendor, I think it was on the Theta, if I remember right, had made some different choices, right, between the size of the requests and the file system. I think they didn't do any aggregation or coalescing. They just sent all the data right out to the file system. But those are the kind of insights that Darshan can help us understand better. All right. So before I hand off things to our friends at the HDF topic, I just want to remind, let's go one more thing, that there are more library interfaces out there. HDF5 and ParallelCF are definitely very common, but you'll see lots of libraries that are targeting different application domains. And hopefully, if you are working in one of these application domains, there's a IO library out there that has already been developed and meets your needs. And if not, you can talk to somebody like me and we can figure out what you might do if you're creating a library for your application. All right. So that maybe a minute or two on questions before I yield the floor.
I think we're caught up on Slack right now.
Fantastic. Well, then I would just say, I hope my enthusiasm for IO has rubbed off on you. I'm happy to say, even though this is my last chance to formally present to you, I am going to be around all day, and I'll be happy to chat with anybody who has any questions about anything.